the delta is 0, so sine of delta is nothing, so all those terms disappear. The only one that's left is when L is 0, in which case your formula will be this, okay? Just this, and your little l here, delta L, is 0. So we now have the total cross section is this. We now have a formula in terms of the phase. Now, so we can actually start working with this. Now, we've got something that we can really start working with. So let's do a particular concrete case. So let's say now we have a spherical well, potential well, and so we're talking low. The incoming particle has low energy and therefore low momentum and therefore large de Broglie wavelength, right? And in that case, you get S wave, spherical wave scattering. Little l is 0, and hence this applies, right? So let's assume. Well, there's two cases. The potential L can be either positive or negative. So, in other words, it's either an attractive potential or repulsive. We'll do the attractive one first. Okay, say its depth or height, depending on attractive or repulsive. Let's say V0, and it's the radius of that potential is A. So outside A, the potential has dropped off to nothing, let's say, effectively. So that's its range, or yeah. Okay. So we'll deal firstly with the attractive case. Now assume the be careful. I've been using this PTL sometimes as potential, an abbreviation for potential, sometimes as particle. So don't be confused. So in this case, as the potential assume the potential goes to 0 as your distance away from the target scattering source goes to infinity, right? So let's assume the potential as a function of r has the following form in this model. So let's say it's attractive, so it has a value of minus V0 in this range when the distance is greater than 0 and less than A, okay? And outside that range, further away than A, little a, let's say the potential is 0, okay? And oh, that's interesting. So assume the energy of the particle is positive. Because if it's negative, then there'll be a potential well. I mean, it gets stuck in the well, it'll become a bound state, and that doesn't scatter. Okay, I mean, we did bound states a lot in the past, but here we're talking about scattering, in context of scattering. So to have scattering, let's assume the energy of the particle is positive. Okay, so E is greater than 0. See, because interested here in scattering. Now, I've written out again from earlier session the STI in terms of chi. Where was chi? Chi. So big R was the radius-dependent part of the Schrödinger wave function, and you defined it as chi over R. So that gave us an equation from the Schrödinger equation in terms of chi of this form. This is your angular momentum form, and you won't, that was sort of thrown at you really. You won't understand where that came from, that term in the Schrödinger equation, until you've done angular momentum, quantum mechanics of, right? Anyway, so you've seen this before from an earlier session, but now we're assuming S wave scattering, so L is 0, so this term drops out. Okay, and so outside the well, in other words, V is 0, so this term drops out, this term drops out, so we're just left with, well, k squared chi here, right? And Now from this was the general form when we did have an L, when L is non-zero. We had this. This is also revision. Like this part here, this is one partial wave. Remember we summed them. Now this whole thing is sort of partial wave analysis, right? A technique used in scattering. So this is just one partial wave, and we can multiply it by some constant, some number, and then or a weighting, if you like, and then add them because Schrödinger equation is a linear equation, so we can add solutions. And this is just one solution. Like this is the R dependent part, and this is the angular dependent part, and the big P here is a Legendre polynomial. Okay, now by definition we define the chi in such that big R, which is this part, the little r, the distance from the target, dependent part. So that means big R is of this form. Okay? Now that's when this is when L is 0. So this L here, just put it as 0. The Legendre polynomial when L is 0 is just 1. Okay, so it disappears. So the L here disappears. So you're just left with this fairly simple form. Right? This is just when L is 0 of this, well, the whole thing. Okay. Now you can rewrite this. Because sine of x is just the sum of two complex numbers, e to the I, x, whatever. So you can rewrite this in the following form. Right? It just becomes this. So you got a sine. Okay, and I could put that as homework. This is quite easy. That's easily done. Getting from here to here is, I don't know, first year, second year, undergrad. So that's pretty easy. But do it anyway as homework. Okay, so you can rewrite this in that form, where your B naught here is just this. Okay, now so what we've done. So we now have an equation for a partial wave here when L is 0, and that equation, we have a wave function. It exists outside the potential region, the well, and we'll do it again inside. So in this region here, we'll get two equations, and then we match again, as we've done many times before. So at the barrier, the boundary, like when R equals A, we'll have the two wave functions have the same value, and we will match their gradients. Their gradients have to be the same as well. And so, but that'll be next session, and as a result of that, we actually get a value, a formula for delta of 0. And we actually get a value for the phase change for delta 0. And knowing that, that will help us know how the particle scatters, right? All right. So till next session to show that.